vector, so then we wouldn't be able to write its component form. Today we're going to get two new pieces of information. Instead of its initial point and its terminal point, I'm going to get the information of the vector's magnitude and its direction. So remember, think about what that means when I give you the magnitude and the direction. I'm telling you how long the vector is, okay? And I'm telling you in what direction it goes, like what that angle is between 0 and 360, so you would be able to draw that angle in any of the four quadrants, okay? And it would be the same thing if we knew like initial and terminal point, and we did terminal minus initial, and then we graphed it. We would then have, its distance and its slope there that we could see. So I'm drawing that same picture. Technically, there's a point over here. I'm drawing that same picture that we keep seeing. So this is a really important picture that you're also thinking about, right? That a vector in standard position is going to have its initial point at the origin, 0, 0. Its direction angle is going to be opening from the positive x-axis, and it's going to open through the four quadrants so that it measures between 0 and 360. And then we know that this vector, like in component form, it has some v sub 1, v sub 2, right? Some horizontal component and vertical component. So we've been sort of drawing that in to create that beautiful picture of a right triangle. Okay. Now you can use this picture of the right triangle to kind of help you with, direction angle. So let's say you forget how to do the direction angle. Okay, draw out that vector wherever it is. You're always going to be drawing those triangles that are part of bow ties and butterflies. And when you go back, it's going to be the inverse tangent of v sub 2 over v sub 1. Okay, so when we're doing direction angle, we're focused on tangent. But if I give you magnitude, okay, so if I'm telling you this distance on the blue piece, and I give you direction, so I'm telling you this angle over here. Okay, now we know these things. Can you tell me what v sub 1, the horizontal component, is? And can you tell me what v sub 2, the vertical component, is? Yes. Using right triangle trig, what two trig functions are we going to be using for v sub 1 and v sub 2? If you know the angle and you know the magnitude. Sine and cosine. So for example, if we were interested in what is our horizontal component, couldn't we say that the cosine of the angle theta is equal to v sub 1 over the magnitude, the adjacent over the hypotenuse? And then if we were really interested in what is actually v sub 1, we could just multiply both sides by the magnitude. So now we can say that the horizontal component is v sub 1, or sorry, not v sub 1, the magnitude of v, my apologies. The magnitude of v times the cosine of the direction angle. So I don't have to know the horizontal component and the vertical component. If I know the magnitude and I know the direction angle, I can find the horizontal component. I can do a similar setup. If I was interested in solving for my vertical component, then I would use sine. So we could say that the sine of theta, the angle, is v sub 2 over the magnitude. And again, multiply both sides by the magnitude. So I'm going to squeeze it in right here. The magnitude of v times the sine of theta. And there I have component form, right? This is my horizontal component. So you can think about it like your V sub 1. And this right here is my vertical component. So that's my V sub 2. So there's now two ways for you to find horizontal and vertical components. If it's like the warm-up and I'm giving you initial and terminal point, do like Abby said, terminal minus initial. If instead I give you information about the vector related to its magnitude and its direction angle, use trig, magnitude times cosine, magnitude times sine. And likewise, you know, like where those are our V sub 1s and our V sub 2s, we could change that into linear combination. Okay. So we did that in the warm-up. For the linear combination, it would be like the magnitude of V times the cosine of theta, because that's my horizontal component. So I'm just going to like protect that with parentheses so you can see there's that coefficient. And then plus the magnitude of V times the sine of theta j. Remember, that one shouldn't be like a whole heck of a lot of work if you've done component form. Right? If you've done component form, you already know what the horizontal and the vertical components are. Okay, how do you feel about this? You got any questions for me? It's just a new way to write component form, given different information, right? Okay, so let's look at some examples, just like, can we apply this just using what we know? Find a component form for these vectors. Magnitude of V is equal to 5. Theta is equal to 30 degrees. And then B, magnitude of V is equal to 2. V goes in the same direction as negative 2i plus 3j. And I'm asking for component form here. I could ask for component form or linear combination form. Right? So this is the one where I want like the angled brackets and the comma. So see if you can look back above and see it, look at your component form and decide what you're going to do to get component form. I give you the magnitude, I give you the direction. I see a lot of people ready to get going on letter A, right? You know the magnitude, you know the direction angle, plug it in. Magnitude times cosine theta is our horizontal component. Magnitude times sine theta is our vertical component. Now I see some people going to their calculators, but may I recall 30 degrees is an angle on the unit circle. So could I ask you to give me the exact values of the components? Yes? Okay, so I'll challenge you, use your chapter 4 knowledge. What is the exact value rather than the calculator value, the decimal value? What's the exact value?
Yeah.
Now you think about 30 degrees and its coordinates. How about that? 5 squared, 3 over 2? 5 over 2? I like that. Anybody start B yet? What's different about B? I gave you the magnitude, but instead of the direction angle, I gave you a vector. Can you find its direction angle? Yeah, it's like the warm-up, right? Go ahead and find the direction angle for, what is it, negative 2I plus 3j. This one, you are going to have to use a calculator. We don't know the inverse tangent of negative 3/2, so you'll get a rounded answer, and that's okay. Anybody find their direction angle? Round it to maybe the nearest tenth. I would do the inverse tangent of 3 over negative 2. What does your calculator say? Negative 56.3. Is that an okay direction angle? No. It's supposed to be between 0 and 360. In which quadrant would that direction angle or that vector lie? Negative 2I plus 3j. Quadrant
2.
2. Left 2, up 3. We're in quadrant 2, so let's just add 180 to this. And so your direction angle is 120. Am I right? 123 point, can I say 7? I'm just going to round to the nearest tenth right now. 123.7? Okay. Like, you can't do that without the calculator. This one, if it's an angle from the unit circle, if it's something you recognize, unit circle, keep it exact. If it's not unit circle stuff, like 3 over negative 2, we don't know a tangent of 3 over negative 2, then let your calculator do the work. Okay. So our component form for V will be what? 2 times the cosine of 123.7 and 2 times the sine of 123.7. And then if you wanted to actually get a decimal value, you could type that into the calculator. I will say, like on your homework, this is going to be 110, 1.664. Okay. On your homework, I'm actually more interested in this answer. Because it's like, did you get the direction angle so that I could see it? And you realize that horizontal is cosine and vertical is sine. You know, then when we need to evaluate it, we can. But I would rather use like this as opposed to negative 1.11 because I just rounded it pretty severely. I mean, I already rounded it when I did the angle, so I really wouldn't want to use these rounded answers later on. Okay. Does anybody have any questions about that? Things, why we did what we did? Yeah, Haley.
Why did we need to find the angle for B? Because if the direction is in the I and J form, I thought that negative 2, 3 would be
Negative 2, 3 would be the component form for this particular vector. So yes, you could change that into component form. But let's say, like, I don't know for certain if that is V or not. So for right now, I'm going to call that U. And if I did the magnitude of u, that would be the square root of 4 plus 9, which is the square root of 13. So it doesn't have the correct magnitude. You could go this way, because last time we talked about unit vectors. You could then scale it down to 1. So divide by the square root of 13, and then multiply it by 2. Okay. But I would guess most people would prefer to just use the direction angle. But yeah, not always would its magnitude match the given magnitude. Okay, make sure you made a little note in your notebook that this is really the answer that we want, right? We're going to reach for this one. You know when I said like what quadrant it was in and I heard some like quadrant 4s out there? What would be different about our answer if we had chosen quadrant 4? The positive and negatives would be flip-flopped, because then the cosine would have been a positive value and the sine in quadrant 4 would have been a negative value. So it does matter that you get that quadrant right so that your components have the correct direction. Okay, good. Let's see. Find the component form for the sum of u and v with directions, angles, theta sub u and theta sub v. So I just want to point this one out because like it seems more complex. So some people sort of like, I don't know what to do with all those numbers. Where should I put all the magnitudes and the angles? So I would just like pay attention. It wants component form. So I want the angled brackets, potentially v sub 1, v sub 2, but I see that I'm getting magnitudes and directions, so I might just be leaving it. Okay, we'll kind of see. Of the sum of u and v with these specific direction angles. So, you know, like when we're adding u plus v, don't we add the horizontal components plus the vertical components? So what I would do for a problem like this is I would write each one in component form. So just like we had done, u equals 2 cosine 45 and 2 sine 45, which I know the cosine and sine of 45 are square root 2 over 2. So that's going to be what? Square root 2, square root 2. I'm using my chapter 4 knowledge. So this is 2 times the square root of 2 over 2, so they cancel. Sine will be the same. Okay. And then I'll do v. So that'll be 5 times the cosine of 90 and 5 times the sine of 90. And I know the cosine of 90 degrees is 0. I'm going 0 left or right. So this is going to be 0, and the sine of 90 is 1. So 5 times 1 is 5. So if I use that magnitude times the cosine of theta and magnitude times the sine of theta, notice both of those angles are on the unit circle, so I'm able to evaluate them. Is it now easy for me to find the component form for the sum? Yeah, this would be like going back to what we had done on Friday. Now I just add the horizontal and the vertical components individually. So it's probably easier on a problem like this to write it in component form first individually and then go back and do the sum. So we want to do u plus v, so that would be square root 2 plus 0 and square root 2 plus 5. And then simplify if I can. So that will be the square root of 2. And however you write this is fine. I normally write a number before a radical, so I would rearrange it. But if you wrote square root 2 plus 5, that would be fine. Okay. So it said find the component form of the sum of u and v. Okay. You certainly could have done like 2 cosine 45 plus 5 sine 90, or sorry, 5 cosine 90. And then done 2 sine 45 plus 5 sine 90. and then all your trig work individually. Questions, concerns? Okay, so now we're going to kind of like dip our toes in the part that maybe our physics friends will remember about vectors, like what is the beauty of a vector? Why do we care about the vector? So vectors can represent different things. Most commonly, the problems that you're going to see are going to be velocity. So the vector itself may be the total velocity, okay? Or it might represent force, so like the total force on a particular object. And you know how like vectors are just like all around different angles. A lot of times there are multiple forces acting on an object, so it's not always just going like straight up, straight down, left or right. So what we can do is we can break up the total velocity or the total force and separate it into like what is its horizontal component, what is its vertical component, because if I'm looking just at like a vertical movement or a horizontal movement, that's the only part of the velocity or force that I really care about. So we're going to do some problems that are going to be, we will call them like application problems, word problems. And this will be our first example. Okay, it's going to be a water balloon with an initial velocity of 40 meters per second, and it's launched at an angle 60 degrees above the horizontal. So find the vertical and horizontal components of the velocity. If you want to jot some little bits of the story down, you can. Okay, now sometimes, like especially like in physics, things might be like spelled out even more specifically, so that you actually have like a specific direction. And we can even see that in some of our math problems. But a lot of ours, I feel like, are kind of open-ended like this with 60 degrees above the horizontal. So if it just tells me an angle and doesn't really say anything otherwise, I kind of assume that it's in that like first quadrant. So I assume it's going to have positive components. Although we could argue that like if we're speaking directionally, we could give one component of velocity a negative to talk about like it was going to the left or it was going down. Okay, so here's what those of us maybe like unfamiliar with this would need to know. And those of you in physics, kind of bear with me, and we might phrase things kind of different, so feel free to ask me if we need clarification. When it says it has an initial velocity of 40 meters per second, sometimes that's also maybe referred to as like a total velocity or just like the velocity. So like all the velocity that object has is 40 meters per second. And this is going to represent your magnitude. So like your total force, your total velocity, the total is going to be the actual magnitude of your vector. So if I'm thinking about an image here, I've got some water balloon being launched 60 degrees above the horizontal. Okay. Then in terms of my vector, I'm calling that 40 meters per second. Okay. And then obviously the angle is maybe going to be your direction angle. You might have to contend with like if I was saying like in a particular direction, like if we were going left and it was 60 degrees above the horizontal, then we might have to think about that reference angle. That's really 120 degrees if the object was moving to the left. But like I said, if it doesn't say, I just kind of assume that it's in the positive direction because that would be easiest for us. Okay, so now we are going to break it down and we're going to say, like there's, if this is the water balloon, there's obviously like the velocity at which I'm throwing it up, but obviously gravity is also acting on it. So there's different forces at play here, and we want to know what's the vertical and the horizontal components. So we basically want to know what's V sub 1 and V sub 2. Well, now it's just a problem where I have magnitude and direction angle. So I know how to find my vertical and horizontal components. Okay. If I just wanted the vertical component, I would do like V sub 2 equals the magnitude of V, which is 40 meters per second, times the sine of 60. Sine of 60 degrees is square root 3 over 2. So that would be 20 square root 3 meters per second. The horizontal component would just be 40 times the cosine of that direction angle. That's 40 times 1/2. So that would be a 20 meters per second. Again, I'll say this. If it's something from the unit circle, we just generally use the unit circle knowledge. We'll leave it exact. If we can't do it on the unit circle, then feel free to grab your calculators and do some calculations. Okay. Are we okay with that? Does anybody have any questions or clarifications? Physics people, you're excited to see it again? No? Yes. Maybe so? Yes, Liam. What's that? How did you calculate? Oh, so you're doing a lot more extra. Okay, because I was like, you would need to know how long it is in the air, right? And we're not necessarily gonna work that. Tomorrow, I think we introduce the work formula. So if you'll remember, work is what? Component of force times, you guys say displacement, but we're gonna call it distance. So we're going to see another formula for that. But we just today need the component forms. Okay. So you have a homework assignment. We've got about 5 minutes right now, 6 minutes. So if you have something from the previous homework assignment that you need to ask about, or if you want to get started on a couple of these just so that you kind of get the feel for what the questions are asking. Remember, I don't necessarily think the math that we're doing is really hard here, but if you slack off and don't put in any effort, it will be really hard to do the quiz on Thursday. You won't know what anything is asking. So make sure that you're taking the time to do some of the practice for me.